So first, let me talk about some filters which are so simple that you may not even recognize them as being filters, but you should certainly be aware that they can do filtering. And that's this class of single reactance low-pass, high-pass filters. So for example, if I have a capacitor in parallel, that's a low-pass filter because that capacitor becomes an open circuit at DC, becomes a short circuit as the frequency gets sufficiently high, and therefore it has low-pass response. Similarly, if I put the capacitor in series, it becomes a high-pass filter because at DC it's an open circuit, at AC it's a short circuit, and that gives us high-pass response. Similarly, if we use an inductor, we can obtain a low-pass or high-pass response by arranging the inductor in the appropriate way. So this is a very simple yet important to recognize class of filters, and using just one component we can get either a low-pass or high-pass response. Now if we want a band-pass or band-stop filter, typically we need at least one capacitor and at least one inductor because we need resonance. In fact, that's what we mean by single resonator. So for example, if we want a bandpass filter, one way to do this is to arrange the L and C in parallel, because that will create an open circuit at some frequency. That impedance will be less than an infinite at other frequencies, and that'll give us a bandpass shaped response. I can do the same thing by arranging L and C in series, and then also have that LC combination in series with the input and output ports. That once again will give me a bandpass response because this arrangement will be a short circuit at the specified frequency of resonance, and it will have relatively higher impedance at other frequencies. Using the exact same strategy, I can arrange to have a band stop response. Again, I can use an LC in series, which is in parallel with the ports, or I can use an LC in parallel, which is in series with the ports. In either case, I'll get a response which looks more like this. So that's a simple way to get bandpass and band stop responses by exploiting the resonance of LC circuits. Now, an important class of filters that use discrete LC components is specified response filters. And by that I mean filters which have certain kinds of response, which we'll later refer to as being Butterworth and Chebyschev and so on. Those designs all consist of a common set of building blocks. For low-pass specified response filters, typically what we will do is we will arrange the capacitor to be in parallel and an inductor in series. And we saw a few slides back that either one of these components alone will of course give us low-pass response. Using them together gives us a little bit more flexibility. Similarly, a high-pass stage in a specified response filter will have an inductor in parallel and a capacitor in series. Either one of these alone would give us high-pass response. Combining the two like this give us a structure which we can use to implement more degrees of freedom. Similarly, for the bandpass and band stop response, we use both types of LC combinations. So in a specified response filter for bandpass response, we will have a parallel LC here and a series LC like so. Either one alone gives us bandpass response. Using them together gives us more degrees of freedom. And similarly for the band stop stage for specified response filters. Okay, so here is perhaps the most common form of specified response filter. It is known as the Butterworth filter. Butterworth filter response is defined by the fact that it is maximally flat. And by that I mean mathematically it's specified in such a way that the response in this part is as flat as it can possibly be. And then beyond the cutoff frequency, we just allow it to be whatever it has to be to achieve that flatness. Now we parameterize all specified response filters in terms of this factor K. K simply describes how many stages we have in the filter. So this filter has twice as many components as this filter. And we see if we use more components, we have more degrees of freedom available, we're able to achieve a tighter response. In other words, we say that this particular filter that has more components in it is able to achieve a tighter response. And as K increases, we can imagine that that shape will become closer and closer to some kind of a nominal brick wall kind of performance. The transducer power gain for a Butterworth response looks like this. This function is 1 plus the ratio of the frequency, omega, divided by the cutoff frequency, which is defined to be the 3 dB point, raised to the power 2 times k, and you take the reciprocal. That is the Butterworth response. So how do we make these filters? And we're starting off talking about low-pass filters. We'll talk about how to extend this to other kinds of responses in a moment. First, you decide k, that is how big the filter will be. And you get that from the response expression. Now, I talked about the response expression. It's this thing. This plot is simply a plot of this expression. So what you do is you decide how fast this curve has to come down. So for example, you might say that, to be 30 dB down, I would like to be only this far away from the cutoff frequency. Or no, maybe I can let this drop a little bit slower, save some components, and let it come out this far. But by using this equation, I can figure out what value of k will get me to my requirement. Next, I use a generating function to determine the normalized component values. Now, what do I mean by normalized component values? Generating functions, such as those described in the book, give you normalized component values, and that means that the filter that you get will have a cutoff frequency of 1 radian per second and will be designed for 1 ohm terminations. Now, you will almost never want a filter that has that kind of cutoff frequency and that impedance. So in general, you have to renormalize the filter, and it's a very simple thing to do. We'll talk about that in a moment. By the way, in the textbook, the generating function, regardless of the response type, is referred to as P sub k. So P sub k are the values of the components in the filter. To obtain the actual component values that you need for your circuit, for the desired cutoff frequency and the desired port impedance, you scale the normalized component values. This is a very simple thing to do. It just consists of multiplying or dividing the normalized components by the right impedances or the right frequencies. And there's several examples of this in the textbook. The best way to learn how to do this is simply to follow those examples. And then finally, you check your work. The best way I know of to check your work is to use simple sophomore level electrical circuit theory. So for example, if you have a filter that looks like this, you can easily check what the impedance is going to be looking this way. It's a series combination of these two things. You can figure out what the impedance is here. It's a parallel combination of this inductor and the thing you just computed. And then you can add the impedance of this capacitor, and then you can put all that in parallel with this inductor. And so you can very quickly tell what the input impedance of this thing is. And you know what the specified impedance is. So you can quickly work out, for example, the reflection coefficient. And from that you can get the transducer power gain. So this is a very, very simple calculation to do. The best way to do this is in MATLAB. You can do it in pen and paper, but it tends to be a lot of tedious number crunching. Instead, just set up a simple MATLAB program, which just walks you through this particular process of stage analysis. And then check and make sure you get the right transducer power gain. Another kind of response is known as the Chebyschev response. Now, I should warn you, Chebyschev, that word gets spelled a lot of different ways. It's a Russian word. There's no obvious English translation for that word, so you see it spelled a lot of different ways. The Chebyschev response is defined by its property of being equiripple, which means that instead of making it as flat as possible through here, instead you constrain the amount by which the response can vary from the nominal flat response. And by allowing it to ripple in some way, you can cause the response to be much, much sharper than you can achieve for a Butterworth filter. So to demonstrate that, here I have a Butterworth filter with k equals 5. Here's the Chebyschev response for k equals 5. In other words, the same number of components in the filter with a ripple defined to be up to 0.1 dB. And you see, using the same number of components, I can achieve a much sharper response. And in fact, if I allow the ripple to be greater, in this case the ripple is up to 0.5 dB, I can achieve even more selectivity. So the Chebyschev response is all about selectivity. It's a trade-off between selectivity and ripple. The more ripple you're willing to accommodate, the greater selectivity you can achieve. Here's a close-up of that previous plot, now just looking at a narrower range. And you can see how this plays out for the different responses. So for Butterworth, that's this curve here. You see that it's maximally flat over the passband, and it drops relatively slowly, whereas Chebyschev with 0.1 dB ripple has a slight amount of ripple in it, and it drops quite a bit faster. And if I allow the ripple to grow, this is Chebychev 0.5 dB ripple, I can make that response drop very fast. So as the amount of ripple I'm willing to tolerate is increased, the selectivity of this filter also gets better. Up to this point, I've been talking about filters in terms of their magnitude response. That is, specifically, I've been showing it as TPG. But phase is also a consideration in filters. If I have some modulation, for example, that's filling the bandpass, I might care about how the phase of the response changes over the bandpass, because that might distort the modulation. So here I'm showing the phase of the different kinds of specified response filters I've considered so far. So here's Butterworth K equals 5, here's Chebychev K equals 5, 0.1 dB ripple, Chebychev K equals 5, 0.5 dB ripple. So these are essentially the same filters with different component values to realize these responses, and I'm showing the phase response. So over the low pass passband here, we see the phase versus frequency is roughly along this line. That's what we refer to as linear phase. That means it has a simple delay, and that's usually what we want in a filter. And then as we enter the stop band, we see that there is some variation in the slope here. It changes, and that infers a different delay. So we see one delay over this part of the frequency response, and a different delay over this part of the frequency response. And that means that we have to be careful if we want to actually use the stop bands. Now, normally we wouldn't use the stop bands, but however, if we look even here, we have some variation from the ideal linear response, and that variation gives rise to dispersion. Dispersion is the property that different frequencies propagate at different rates through the filter. And again, that could be a problem for modulation. So phase response is something you also have to consider in filter design. The way we normally characterize this dispersion is through a parameter known as group delay, or group delay variation. And the group delay is simply the derivative of the phase response with respect to frequency, which is just a measurement of the delay, as I just pointed out. So we can actually plot that delay. Again, this is simply the slope of the phase response. And the nominal group delay variation, of course, is perfectly flat. That would mean there's no dispersion. This filter could have no deleterious effect on modulations, which are phase sensitive. However, all practical filters have some dispersion, and that dispersion is characterized here as the group delay variation. So here I'm showing it for Butterworth, K equals 5, Chebychev K equals 5 with 0.1 dB ripple, Chebychev K equals 5 with 0.5 dB ripple. And the thing you see, which might not be too surprising, is that the best dispersion, that is the minimum group delay variation, is given by the Butterworth response, the maximally flat response. And if I try to achieve greater selectivity, the trade-off is I have greater group delay variation. So we see the Chebychev peak group delay variation is much greater than the peak group delay variation for the Butterworth filter. So this is frequently a consideration in selecting a filter response. Now let me say some more about different responses and topological variants. By topological variants, I just mean different ways to arrange the L's and C's in a filter. So to remind you, Butterworth was maximally flat. Chebychev was Equiripple, which gives you greater selectivity. The Gaussian response is defined to have minimum group delay in the passband. So that doesn't mean it has minimum dispersion. It just means that the propagation time through the filter is minimized. It's a constraint on the slope of the phase response. And the trade-off is that you get a little bit better dispersion properties, but a little bit worse selectivity. The Bessel response, you explicitly try to make the filter have linear phase response. So that means this is the filter response that will give you the minimum group delay variation. And this is what you want if you need flat time delay. And RF engineers use this term quite a bit. Flat time delay simply means no dispersion, minimum distortion in phase versus frequency. Unfortunately, this gives you the worst possible selectivity. So when you're shopping for filters and you see filters been specified as being either Bessel or flat time delay, means the same thing, you know what the trade-off is. Another choice is elliptic response. Elliptic just refers to the mathematical function which is represented by this kind of response. An elliptic response is Equiripple, just like Chebyschev is, but it's Equiripple in both the passband and the stop bands. Chebyschev is Equiripple only in the passband. Elliptic is Equiripple in both the passband and the stop bands. So the response looks something like this. Here's the passband, here's the stop band level. So it looks like this. And then this ripple amount is constrained to be equal in both the passband and the stop bands. That gives you the fastest possible transition between passband and stop band. So if you're concerned about how fast you go from the passband to the stop band, elliptic is the way to go. Relatively insensitive to component value variations, which is another reason why this particular response shows up. If you're concerned about component values not being accurate enough, an Equiripple response will tend to mitigate some of that concern. This response tends to be awesome for the anti-aliasing filter that goes in front of analog to digital converters. So as you are no doubt aware, if you have an analog to digital converter, you have to be careful to put some kind of response in front of that filter in order to eliminate everything that would violate the Nyquist criterion for sampling. And a very nice feature in that filter would be as if you can have some kind of passband response and then come down very hard and then go like this. Elliptic response goes by a couple other names. It's also known as a Cauer response, also known as a Zolotarev response. So all those things mean more or less the same thing. And then topological variance. So I showed you the various structures, the component arrangements that give you the standard responses, and then just said, well, you just change the values to get these responses. But you can change the design of the circuit to result in more reasonable component values. I'm not explaining at all about how to do that. I'm simply pointing out that sometimes you can rearrange the way the inductors and capacitors are organized in the netlist to achieve better component values. And this is where filter design engineers really contribute to RF design, as they can normally figure out ways to get a specified response in a filter which might be more compact or have more reasonable component values. Now, to this point, I've talked only about low-pass filters. However, we're of course interested in high pass, we're interested in band pass and band stop. Getting those kinds of responses is surprisingly easy. All other responses can be obtained by modifying the low-pass filter. So if you know what the low-pass filter looks like, you can transform that very simply into a high-pass filter, a band-pass filter, or a band-stop filter. And the strategy goes like this. To go from low-pass to high-pass response, you take those normalized component values and you simply take the reciprocal of those values. So if you design a low-pass filter and you get the normalized component values for whatever response you seek, simply take the reciprocal of those values and design the filter, and it will be the corresponding high-pass response. Very straightforward idea. If you want to go from low-pass to band-pass, then what you do instead is you resonate each segment to the desired center frequency. What do I mean by resonate? Well, that means whenever you see a capacitor, you're going to add an inductor. Whenever you see an inductor, you're going to add a capacitor. And that capacitor and inductor will be either in parallel or series, depending on which branch of the circuit it appears in. If you want a band stop filter, the easiest way to do that is to design a high pass filter and then resonate each segment to the desired center frequency. So low pass and then resonate, we get band pass. High pass and then resonate, we get band stop. Now, this particular procedure of resonating each segment is perhaps a little bit confusing. Even though the fundamental idea is very simple, sometimes students get confused about how precisely to resonate each one of those segments. And I found the best way to explain it is simply by example. So there are examples of each one of these procedures in the textbook. They're very simple, I think, to follow. So my suggestion is to look at each one of those examples to clearly understand what each one of these procedures really entails. And then I'll point out that this works for any response. In other words, if I design a Chebyschev low-pass filter, the corresponding Chebyschev high-pass, bandpass, and bandstop filters can be obtained in exactly this way.